Hello, my dear friends. So, my name is Shailendra Gupta, and I'm continuing giving lecture on the subject electric drive for electrical engineering students. So, till now, I have discussed the basic logic diagram for implementation of closed loop speed control for DC motor. So, before going into the design of these controllers, I wanted to discuss the basic terminologies that will repeatedly come while we design our controller. So let us just get started. Okay, so here we are having a system. In our case, it is a DC motor. So there is a one input and one output. In our DC drive case, the input is the reference speed, reference rotary speed of the DC motor, and the output is the actual DC motor speed. So, as per the basic understanding of this control system, the actual speed of the DC motor should be equal to the reference speed. As we change the reference speed, the DC motor speed should change. So, to implement this, we should know about our system. Uh, so, let us first study a first order system. So, as per first order system, we can make a diagram. So this is a first order system. So it will be having again, let us say K by S. To this there will be an input. The output will be processed through this gain, and there will be a feedback. So when we solve this uh, with the general equation of this is output upon input is equal to K by S divided by 1 plus K by S into 1. 1 is the feedback control. So this is negative feedback control, mind you. So solving this, so this will be equal to when I solve this will come K S plus K, taking K constant from the numerator and denominator, so it will become 1 upon S by K plus 1, which could be equal to 1 upon Ts plus 1. Here T is equal to 1 by K and the time constant. So let us just analyze this first order system. This first order system has a single pole at S is equal to minus 1 by T. So for input has to be a step input. Let us take input as to be a step function. So Laplace transform of this input will be, so if we take the Laplace transform, it will be 1 by S. So our output will be equal to output Laplace transform will be equal to 1 upon 1 plus St into this input. So it will be 1 by S. Now simplifying this, so this could be it will be minus t upon 1 plus st plus 1 by s. If we solve this, now taking the Laplace inverse of output equal to Laplace inverse of minus t upon 1 plus st plus Laplace inverse of 1 by s. So here it will be output in time domain will be equal to Laplace inverse of minus t upon 1 plus st will be e raised to power minus t by t, and Laplace inverse of 1 by s, there will be a minus sign here. Laplace inverse of 1 by s will be 1. So if we like to draw this, then we can easily draw this. So let us first draw the input. So our input is like this. It is a step input at t is equal to 0. So this is our input. Now what is our output? At t is equal to 0, this term will be 1, and 1 minus 1, it will be 0. So our output will start from here, from this point. So as t prolongs, it will be an exponential function with t as time constant. So at t is equal to t second, so this is time. At t is equal to t seconds, the function will achieve 63.3% of its value. So we can see that when this input is increasing instantaneously at t is equal to 0, the output is achieving the same value as input, but with a time delay. Here the delay is this time constant. So after this time, we can treat the output as to be equal to input. So first order system will create a delay in the system. This is the first concept, the time period concept, which should be understood by each student, that how the system is having a delay in a first order system. So now let us take a second order system. We have done first order system. So let us clear this because there is no more space. So we should clear this. Now let us study a second order system. So a second order system. What is the second order system? A second order system will be having a two poles. The open loop Gale will have two poles, st plus 1. So here it is having a, this is a gain. So we will have a input, output, and there will be a feedback. So now let us solve this. So the transfer function output upon input will become 1 upon s st plus 1 upon 1 plus GSHS. So here GS is s st plus 1 into 1. So this can be taken as 1 upon s into st plus 1 plus 1. So it will be 1 upon s square t plus s plus 1. So taking t out of this, so it will be 1 upon t divided by s square plus s by t plus 1 by t. So here it is a second order system, the transfer function of second order system. This can be taken as to be this can compare to a general expression of a second order system. The transfer function is, it could be compared to omega n square upon s square plus 2 zeta omega s plus omega n whole square. So here we can see that omega n is equal to 1 upon root t, and zeta is equal to this is 1 by t into 2 omega n. So we can solve for this, but we should know the poles of these transfer functions. So here the pole could be written as s1 comma s2. It will be minus zeta omega n plus minus j under root it will be omega n under root 1 minus zeta whole square. Okay, these will be the two poles of this transfer function. I want all the students to understand these functions: zeta, omega n, and this we can take it as omega d, the damping frequency. So these three terms should be very much should be clear to all the students. What are these terms? Let us discuss. First of all, omega n. Okay, so omega n. Omega n is the natural frequency of the this system. So what is the natural frequency? Actually, every system has got its own natural frequency. If that system interacts with a wave which is having the same frequency, then a resonance is created in the system. So our system will also be having a natural frequency. Now, what is zeta and omega d? To understand the term zeta and omega d, we need to take the Laplace inverse of the transfer function. this transfer function. So let's take a step input, and as previously discussed, the Laplace of step input will be 1 by s. So we can take um, our output will become, this will become um, omega n whole square divided by s plus s1 s plus s2 into 1 by s. So when we take the Laplace inverse of this function, so the Laplace inverse of this function will come out to be as follows. This will be in time domain. This will 1 minus e raised to power zeta omega and t divided by under root 1 minus zeta square sine of the omega d t plus tan inverse under root 1 minus zeta square upon zeta. So I want to all of you to concentrate on this term. Let me just zoom it out. So this output function, this is similar to a function which looks like something like this: 1 minus a sine omega t plus phi. So what is this? A sinusoidal signal. Sorry. So a sinusoidal signal is overlapping with value 1. So let us say a is a constant. What is this? A is constant. Okay. So our sine omega t plus phi, this will lie between -1 to 1. When added to 1, the whole function will now become, this will be lie from 2 to 0. Okay. So we can draw this function. So this function will look like, has to be like this. So it will be a sinusoidal function, which will be having this will be a sinusoidal function. This is our output. What is this? This is our output form. Mind you, we have drawn just this 1 minus a sine omega t plus phi. So this sinusoidal signal will be having a frequency of omega, which is here omega. Omega is what? Omega is the damping frequency that we have defined earlier. So now let us just analyze this equation. So here, mind you, this a, This A is this thing. This A will be constant when zeta will be equal to 0. At zeta is equal to 0, what will happen? This denominator will be 1 and this function will be 1. And this omega d will become omega n. We can see this. So omega d is equal to omega n into 1 minus zeta square. So at zeta is equal to 0, omega d will be equal to omega n. That is the natural frequency. Now the damping frequency is natural frequency. Is attaining the natural frequency of the system, and A is 1. So this is exactly the output for zeta equal to, this will be having an output at zeta is equal to 0. So when the damping constant, this zeta is 0, then the output is oscillating in nature. And mind you, we have given an input that is stepped. This was our input. So this is our input. And what we are getting? We are getting an output that is oscillating around this input. But our objective was to control our output as to be equal to input. But here it is not happening. Why? Because zeta was equal to 0. Now let us just increase this zeta. So what will happen when zeta is increased? So it will this A will start decreasing as per time, because now this is real value 0.1. So it will be multiplied with time. As time increases, this A will start reduce. Therefore, this sine term will start decaying, and as t increases to a sufficient value, this function will lose its control over 1. So it will look like this. Sorry. Okay. So it will look like, so let us say an exponential function. Let us draw an exponential function. So this function is decaying. Okay. So what is this? This function is e raised to power minus zeta omega n t. Okay, so this function is decreasing. So our sine will be damped between this layer. So it will become like this. So our new function will be like this. The sinusoidal signal will start damping out. Okay. So this is for zeta is equal to, let us say, 0.1. So as we increase our zeta, so this band of e raised to power minus zeta omega n will be having a, 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 a smaller time constant. So as this band shrinks, this value will also shrink. So it is analyzed that at zeta is equal to 0.707, that is 1 upon root 2, the system gives best response. So at 0.707, let us say, it will behave like this. So it will be having best response. So this is for uh, zeta is equal to 0.707, which is equal to 1 by root 2. And if we go beyond zeta, then it will become critically damped. Let us change the color. So let us take this color. So uh, for a critically damped system, there will be no exact oscillation. So it is a critically damped, but you mind you that the system will having will the output will be equal to input after a pretty large value. Okay, here for zeta is smaller than 1, the value of output was uh, very uh, the rise time was quite less for zeta is smaller than 1. But for critically damped, when zeta was equal to 1, this output is achieving the input after quite some time. So this is what this is for zeta is equal to 1, not a critically damped system. So this is what the meaning of uh, zeta and omega. So zeta is the damping constant. How fast the sinusoidal signals, the oscillations in the system are damped out, and omega d is the frequency at which it will oscillate. So our uh, our strategy in the control system is to decide the zeta and omega n such that the system is having best response. Best response means the zeta should be having 0.707 value. So we should be having an output should be uh, let us take our black ink, the general ink. So the output will be equal to input. This is our first criteria. Okay, so then it means the transfer function will be having a value of 1. Okay, um, but this this the output will be equal to input uh, only for a limited range of input change. Uh, what we call it as to be bandwidth. So the range between which the output is equal to input. It means if input varies at that much frequency, then only the output will trace this input. Otherwise, it will not. We can plot this. How it will look like this. So if we take our transfer function, so here it is 1. We need it to be 1. And let us trace it versus log omega. And omega is what? The frequency of the input. So this any control system could be designed for a limited bandwidth. It means for a certain omega, this transfer function will be 1. But after this, it will start decaying. Okay. So again, the same rule is there. Uh, until and unless this transfer function value is 707, we consider the controller to be working fine. So this is called the bandwidth of the system. This is nearly 1 by root 2. So as input changes, the transfer function should be near to uh, should be higher than 1 by root 2. That is 70.7% of the uh, of the input. If output is tracing the input up to 70.7%, then we can treat as to be a good response. So we can consider that to be a bandwidth. So we need to design our control system to achieve this uh, bandwidth. So in the next lecture, I will discuss that exactly how to just proceed while designing our uh, controller, speed controller. But before that, let us just note that what we need to understand. We need to understand the time constant phenomena. What does the time constant mean? The second thing is what is a damping coefficient, zeta. Third thing is the natural frequency, understanding the meaning of natural frequency, and last is the damping frequency. Okay, thank you for now. We will meet in the next lecture. Thank you.